Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be back.
So imagine trying to pump boiling, highly corrosive acid that just so happens to be filled with really sharp, abrasive grit.
Yeah, that is a nightmare scenario for a standard centrifugal pump.
Right. I mean, a metal impeller would just chew itself to pieces in a matter of hours. The seals dissolve, the metal pits, and boom, you have a catastrophic leak.
Exactly.
So today we are, setting aside the microcontrollers and the software updates. We are going back to the raw, unfiltered fundamentals of engineering. Our mission for this deep dive is to really explore the hidden physical intelligence of machines.
It's fascinating stuff when you really look at it.
It is. We are digging into these legacy blueprints to see how pneumatic, hydraulic, and mechanical systems move impossible materials, how they multiply force and self-regulate without a single microchip.
And honestly, it really is a masterclass in physical problem solving. When you analyze these historical schematics, you realize that long before we had code to tell a machine what to do, the physics themselves were the code.
Right. The geometry, the fluid dynamics.
Exactly, the thermodynamics. They all acted together to create systems that are just inherently robust. And for any engineer listening to this who might be staring down a complex physical problem at the workbench right now, mastering these foundational concepts is just critical.
Yeah, because we get so used to just, slapping a sensor on a problem, right?
Yeah.
We completely forget how to solve it mechanically.
We do. We really do.
So that is the exact lesson we want to extract today. You don't always need a PID controller to handle a harsh environment. Sometimes you just need a radically different approach to fluid dynamics.
Right, because before you can actuate any massive mechanism, you have to actually move the fluid.
Exactly. So let's look at that hostile acid scenario I mentioned. When standard pumps fail, the engineering constraint shifts entirely. You basically have to protect the working components from the fluid itself.
We do, yeah.
I was looking at the schematics you sent over for the squeegee pump, and the elegance of it is striking. The core mechanism is literally just a U-shaped flexible tube, usually something tough like neoprene or vulcanized rubber.
Yeah, and the brilliance there is the complete isolation. The fluid, no matter how harsh or abrasive, only ever touches the inside of that flexible tube.
Wow, so it never makes contact with the metal working parts.
Never. Not the bearings, not the lubricating oil, nothing. To physically move the fluid, they mount cams on a central driven shaft. And as that shaft rotates, the cams push compression blocks progressively against the tube.
Oh, I see. So it's squeezing the tube completely shut, from the intake side all the way over to the discharge side, block by block.
You got it.
It's very similar to the human digestive tract, right? Like using peristalsis, or, well, on a more mechanical level, it's just like squeezing a tube of toothpaste from the bottom up.
That's exactly it.
You're forcing the material out without ever actually touching the paste inside.
That analogy holds up really well, actually, but we also have to factor in what happens behind that compression point.
Okay, what do you mean?
Well, as the cam passes and the block releases its pressure, that synthetic tube naturally expands back to its original circular diameter. It does this because it is fully encased and constrained by the pump housing.
Right.
And that rapid expansion creates a massive vacuum on the intake side. Specifically, it pulls a 25-inch mercury vacuum.
Wait, a 25-inch mercury vacuum?
Yeah.
That is intense. That is approaching absolute vacuum. That requires incredible structural resilience from the rubber tube so it doesn't just, collapse under atmospheric pressure.
It really does. And because it pulls such a hard vacuum, the atmospheric pressure pushing on the supply tank forces the heavy fluid into the tube incredibly fast for the next cycle.
That is brilliant. And the specs on this are substantial for such a simple geometric concept, right?
Oh, definitely.
It handles up to 15 gallons per minute, pushing against 50 pounds per square inch. Plus, you can drive it clockwise or counterclockwise just by reversing the shaft rotation.
Right. But isolation isn't the only way to handle hostile materials. Let's pivot to a slightly different challenge. What if you aren't just dealing with corrosives, but literal sand and scale?
That sounds like a nightmare.
It is. For that, engineers in the mid-20th century developed the gearless marine pump. It was originally built to handle bilge water mixed with abrasive solvents. But its true claim to fame is that it passes solid grit without destroying itself.
Because a standard bronze impeller would suffer severe plastic fracture in that environment, right? The sand would just gouge the metal.
Exactly. It would destroy the tight tolerances you need to maintain pressure.
So how does a marine pump survive that kind of abuse?
It comes down to elastic deformation versus plastic fracture. The impeller in this pump is not metal at all. It is made from pressure vulcanized, laminated layers of a synthetic material called high-car.
Okay.
And it's cured to be about 85 to 90% hard. So when a piece of sharp silica sand gets caught between the housing and the impeller, a metal impeller would try to crush it and get gouged. But the high-car impeller has this slight synthetic elasticity.
Oh, I get it. So it simply deforms around the grain of sand.
Exactly.
It yields to the grit, rolls it through the discharge port, and then instantly rebounds to its original shape to maintain the seal.
Yep. It literally just shrugs off the abrasives. And it delivers capacities from 1 to 12 GPM at pressures up to 60 PSI.
That is just a brilliant application of material science solving a mechanical problem.
It really is. And moving along the spectrum of difficult fluids, we have to look at the single and double helix pump. This design tackles non-pourable pastes.
Like fluids heavily packed with abrasives in suspension. This specific schematic actually made me stop and reconsider how we design positive displacement pumps. I mean, it has exactly one moving part.
Just one.
Yeah, a single helix rotor, usually machined from tool steel, which spins inside a stator made of high-car or natural rubber. But the stator isn't a simple cylinder, right? It has a double internal helix shape.
The geometry is fascinating.
Mm.
As that single helix rotor turns inside the double helix stator, it creates a series of sealed, distinct cavities.
Okay.
And as rotation continues, these sealed cavities progress continuously from the suction end straight to the discharge end.
So the working fluid is trapped in a void that physically travels down the length of the pump.
Right.
So it's basically like a piston moving through a cylinder of infinite length.
That's a great way to put it. And taking that infinite piston concept a step further, it means you achieve a continuous, perfectly uniform flow.
Oh, so you completely eliminate the pulsation you would normally get from a standard reciprocating piston pump.
Exactly. There are no valves to clog. And because the seal lines are so tight, the pump actually self-primes at up to 28 feet of suction lift.
Wow.
And furthermore, the head pressure it develops is completely independent of its rotational speed. The volumetric capacity just remains directly proportional to the speed.
Which makes modeling this pump in a larger system incredibly reliable for an engineer. The legacy documentation notes that the slippage, the tiny amount of fluid that leaks back past the seal lines, is purely a function of the fluid's viscosity and the back pressure.
It is entirely mathematically predictable. You can even pass solid particles almost an inch in diameter through their larger models, moving 150 GPM up to 200 PSI.
That predictability is just non-negotiable for engineers. But there is one more fluid challenge we need to cover before we move on to actuation, and that is high-viscosity petroleum, specifically boiler fuel.
Right. Engineers rely heavily on the internal screw pump for this application.
Because you absolutely need a perfectly smooth, pulseless flow of oil for a commercial boiler, right? I mean, if the fuel delivery pulses, the combustion flame pulses.
And a pulsing flame causes wildly inefficient heat transfer. But even beyond the thermodynamics, a pulsing flow in a heavy oil system creates water hammer.
Oh yeah, water hammer is brutal.
It introduces severe hydraulic shock waves that travel through the heavy piping. Over time, that leads to structural fatigue, blown gaskets, fractured fittings. So the low vibration of the screw pump protects the entire infrastructure.
And the mechanical layout of that internal screw pump is what makes it so stable. The pumping screws are mounted on parallel shafts. They draw liquid from both the front and rear ends of the pump housing simultaneously.
Right, driving the fluid toward the center for discharge.
Exactly. Because it pushes the heavy oil from the outside in, the hydraulic thrust forces acting on the shafts completely cancel each other out.
That balanced pumping action is honestly a stroke of structural genius. Because the axial force is neutralized, you don't even need massive thrust bearings on the shafts to keep them from blowing out the back of the housing.
Unless you were mounting the pump at a steep vertical angle, I guess?
Well, yes.
And to keep the pumping screws from grinding against each other under load, they are timed by a pair of precision-cut herringbone gears.
Those gears are self-centering.
Yeah, they absorb the rotational torque so the intermeshing screws don't experience side wear while they move the oil. You end up with a pump that is just whisper quiet, vibration-free, and incredibly durable.
It's beautiful engineering.
So, okay, we've figured out how to move these impossible fluids safely, but moving fluid is really only half the battle. If we want to actually do work like lifting a multi-ton load or actuating a massive piece of machinery, we need to weaponize that fluid pressure.
Right.
How do we take a standard low-pressure flow and turn it into massive, concentrated mechanical force?
This is the transition from fluid dynamics into pure mechanical actuation. Suppose you have a standard low-pressure hydraulic circuit running your factory floor, right?
Okay, sure.
But a specific pressing machine requires massive, concentrated force. Installing a completely separate high-pressure pump system is expensive, it's heavy, and adds unnecessary complexity.
So what do they do instead?
Instead, engineers utilize a hydraulic booster, commonly known as an intensifier.
Ah, right. The intensifier takes a high volume of low-pressure fluid and converts it into a low volume of incredibly high-pressure fluid. The multi-plunger unit, detailed in our sources, achieves a maximum discharge pressure of 7,500 psi.
And it does so without a dedicated motor.
Really?
Yeah, this specific intensifier relies on 6 double-acting pistons. A central, hydraulically balanced valve admits the low-pressure factory oil to these 6 pistons in a very specific time sequence.
I see. So by staggering the strokes of 6 independent pistons, the high-pressure output flow remains completely smooth and uninterrupted.
Exactly. And the downstream advantage of bumping your system up to 7,500 psi is what it allows you to do with your end effectors. Operating at that extreme pressure means you can use much smaller operating rams and cylinders to achieve the exact same crushing force.
Oh, that makes sense. And the size of the ram is critical when we discuss the physics of inertia, isn't it?
Very critical. A massive heavy steel ram requires a tremendous amount of energy just to accelerate, an equally massive braking force to stop it.
Right. But by utilizing 7,500 psi and shrinking the physical dimensions of the cylinders, the inertia effects of those operating rams are drastically reduced.
Exactly. The machinery can reverse direction and operate at much higher speeds with far greater energetic efficiency.
And once we have that high-pressure cylinder moving, the way we link that linear push or pull motion to the actual load kind of defines the entire character of the machine.
Oh, absolutely. It isn't always a direct, straight push. You can link a simple push cylinder using all 3 classes of levers to change both the direction and the multiplication of the force.
Let's break down exactly how those linkages modify the force. Like if you need rotational torque rather than a straight push, you don't just attach the rod to a wheel, right? You use a gear sector.
Right. By machining teeth into the side of the piston rod, basically turning it into a rack and mating it perpendicularly to a gear sector, you translate that high-force linear stroke directly into massive rotational shaft power.
And if an engineer needs an extreme mechanical advantage in a highly confined space, they might just bypass levers entirely and use wedges.
Wedges are incredibly powerful. A hydraulic cylinder driving a steel wedge under a load acts as a moving inclined plane. It multiplies the lifting force exponentially compared to a direct vertical push.
Albeit over a much shorter stroke.
True. Alternatively, you can drive a steep screw nut to produce slow, highly controlled shaft rotation.
Okay, let's ground this in a real-world application that layers these hydraulic and mechanical concepts together. The historical documentation outlines the steering system of a 300-horsepower diesel tractor.
Yeah, that's a beast of a machine.
A 300-horsepower diesel is massive. The engine-driven pump delivers 55 gallons per minute at 1,200 psi, and it dedicates a 15 GPM flow entirely to the steering circuit.
The linkage design here is what's truly fascinating. The steering drive to each wheel is physically mechanically linked.
Right, they use this complex arrangement of Stevenson links, bell cranks, and tie rods to mechanically select between front-wheel steering, forward-wheel steering, or crab steering.
And then that 1,200 psi of hydraulic power is layered on top to amplify the driver's manual effort. The integration of those two systems, the fluid power and the solid geometry, is just a masterclass in safety design.
Okay, I actually have to challenge the engineering logic on this one, though.
Oh, how so?
Well, if we have 1,200 psi of hydraulic power and a constant 15 gallons a minute of flow, why bother with the massive, heavy mechanical tie rods and bell cranks at all? I mean, it seems incredibly redundant.
I can see why you'd think that.
Why not just place an independent hydraulic cylinder on each wheel and steer them purely with fluid pressure?
It does seem redundant until you analyze the failure modes. It really comes down to the core philosophy of heavy machinery design. Absolute fail-safes and forced synchronization.
Okay, forced synchronization.
Yeah, if you rely purely on independent fluid cylinders to steer a 300-horsepower machine, any slight variance in seal friction or a tiny internal bypass leak or a momentary pressure drop in one line.
It could cause one wheel to turn slightly less than the other.
Exactly. And at those speeds and weights, a misaligned wheel is catastrophic.
Ah, I see. So the mechanical tie rods force the wheels to remain in perfect geometric lockstep. The fluid is physically incapable of overriding the solid geometry of the steel links.
Precisely. The mechanical linkage ensures absolute safety and synchronization. The hydraulic system is there strictly as a muscular assist, so the operator doesn't have to physically fight the sheer weight of the vehicle.
That makes total sense. If the hydraulic pump fails completely, the operator still maintains full physical control of the steering wheels.
Right, it requires a lot more upper body strength, but the geometry acts as an unbreakable fail-safe.
Which brings us perfectly to the final piece of the puzzle for today's deep dive. Power without control is just a disaster waiting to happen.
Absolutely.
How do these massive, purely physical systems monitor their own state, provide feedback, and self-regulate without a digital control unit?
We often assume feedback loops are exclusively a modern digital concept, like sensors sending varying voltages to a microprocessor.
Right, that's what we're used to.
But analog mechanical feedback loops are incredibly sophisticated. They use the physical properties of the system itself to regulate it. Consider the foot-controlled braking system on a heavy industrial crane.
Oh, the schematic is a brilliant example of a closed-loop mechanical logic gate. When the crane operator pushes the master cylinder foot pedal, it sends hydraulic fluid to a releasing cylinder.
But that cylinder doesn't push the brake shoes against the drum.
No, instead it compresses a massive brake-setting spring.
And here is where the logic gate triggers, based on line pressure. Once that heavy spring is fully compressed, the fluid reaches a hard physical stop. This causes the pressure in the hydraulic line to spike sharply.
And that pressure spike mechanically trips a hydraulic pressure switch.
Exactly. That switch completes a local electrical circuit, which energizes a magnetic check valve.
And when that magnetic check valve snaps shut, it physically traps the hydraulic fluid inside the releasing cylinder. The heavy spring is now held in its compressed state by the trapped, incompressible fluid.
Right, so as long as the operator keeps their foot resting on the pedal, the system is armed, but the brakes remain released.
But the moment they lift their foot, the check valve opens, the trapped fluid vents, and a secondary brake-releasing spring yanks the lever arm down, instantly dropping the heavy brake shoes onto the drum.
It is entirely fail-safe by design. Think about it. If electrical power is lost, the magnetic valve drops open and the brakes engage.
And if hydraulic pressure is lost, the fluid vents and the massive spring forces the brakes to engage. The system literally uses the fluid's own pressure state as the physical switch to confirm the mechanism is armed.
It's just brilliant.
Speaking of remote physical states, we have to talk about the legacy analog dashboard instruments in automobiles.
Oh, yes.
Specifically, the oil pressure, engine temperature, and gasoline gauges. This is just a masterstroke of design. For years, I assumed there was a varying voltage being sent down a wire that moved a magnetic needle on the dash, much like a modern digital to analog converter.
That's a very common assumption.
But this legacy system doesn't send data at all.
No, it doesn't. It utilizes a bimetal element system. It relies entirely on the simple thermal expansion properties of metals.
Right, so for you listening who haven't worked with them, a bimetal strip is simply two different metals fused together. Because they have different coefficients of thermal expansion, heating the strip causes one metal to expand faster than the other.
Which forces the entire strip to physically bend.
Exactly. So in this system, you have a sender unit bolted into the hot engine block. A grounded contact completes a circuit that powers a tiny heater wire wrapped around a bimetal strip.
And as the engine block gets hot, the strip heats up, bends, and physically pulls away from the grounded contact.
And that breaks the electrical circuit.
Right. And once the circuit breaks, the tiny heater turns off. So the bimetal strip cools down, bends back, touches the contact, completes the circuit, and the heater turns on again.
It just sits there rapidly clicking on and off, establishing a precise, pulsating thermal equilibrium governed entirely by the ambient heat of the engine block.
But the true genius is on the receiver end.
Yes. Okay, let's unpack this because this was an absolute aha moment for me. The gauge on your dashboard contains the exact same heater coil wrapped around the exact same bimetal strip.
Yep.
And because the dashboard gauge and the engine sender are wired in series, they share the exact same pulses of electrical current.
So as the sender in the engine clicks on and off, the dashboard strip heats and cools at the exact same rate,
causing it to bend in perfect unison. I mean, it isn't sending digital data or a voltage reading to a computer screen. It is literally transmitting a physical temperature state to remotely bend a piece of metal on your dashboard in real time.
It's amazing, isn't it? The deflections of that dashboard bimetal strip are simply connected to a mechanical linkage that moves the painted pointer over the scale. It is a remote, synchronized physical mirror.
It is analog physical telemetry, and they use the exact same mechanism for oil pressure and gas tank levels, too.
Oh, yeah. The only difference is that instead of the ambient engine heat affecting the sender, a physical diaphragm in the oil line or a float in the gas tank applies physical tension to the sender's bimetal strip.
So that preloaded tension changes how much heat is required to break the circuit, which alters the pulse rate, mirroring the physical pressure or fluid level right on the dash.
Exactly right. Now, wrapping up our look at thermal regulation, we really must examine the thermostatic controls used in heavy-duty gas ranges and refrigeration plants.
The engineering challenge here is using temperature to actuate a mechanical valve reliably over thousands of cycles.
Right. And the sources outline a gas range control that uses a sealed metal bellows system. It consists of a temperature-sensing bulb inside the oven, connected by a long capillary tube to a flexible corrugated metal bellows at the gas valve.
Okay, so as the bulb heats up, the fluid inside expands, travels down the capillary tube, and physically pushes the bellows open.
Exactly. That mechanical expansion moves a series of levers that choke off the gas flow. But as always, the devil is in the details.
Naturally.
First, the fluid choice. Because this operates in a commercial kitchen near food, engineers selected chlorinated diphenol as the expansion liquid.
Chlorinated diphenol?
Yes, it possesses a specific boiling point and thermal expansion curve tailored for oven temperatures. But crucially, it is entirely non-toxic and non-flammable. If a line gets pinched or fractured, the thermal failsafe won't cause a grease fire.
That's incredibly smart. But the most impressive engineering choice to me is the geometry of the bellows themselves. They don't feel the inside of the bellows with the expanding fluid.
No, they don't.
They seal the chlorinated diphenol outside the bellows, housing it within a rigid surrounding cup.
Right, and to a layman that might seem counterintuitive.
Yeah.
But an engineer looks at the stress profiles. The bellows is typically made of thin phosphor bronze, which is very susceptible to metal fatigue over time, especially at high temperatures.
Exactly. Because if the fluid was inside the bellows pushing outward, the thin metal corrugations would be stretched to their absolute maximum limit at high cooking temperatures.
You would be applying maximum mechanical stress at the exact moment the metal is hottest and most structurally vulnerable.
But by putting the fluid on the outside, compressing the bellows inward against a heavy internal spring, the bellows actually bottoms out and rests fully relaxed against its internal stops at normal room temperatures.
This flips the stress profile completely. The maximum physical working stress on the thin metal bellows occurs at room temperature, when the bronze is cold, rigid, and least susceptible to fatigue.
Wow.
At elevated working temperatures, the expansion of the liquid compresses the bellows against the spring, distributing the load. You are protecting the most delicate component from high-stress fatigue precisely when it is operating in its harshest thermal environment.
It's the kind of foresight that separates a product that lasts 3 years from a mechanism that operates daily for 50 years without requiring a single maintenance call.
Absolutely. And, stepping back to view the broader implications of all this deep dive really underscores a vital philosophy for modern design.
What's that?
Well, today, the immediate reflex in the industry is to solve a complex physical problem by throwing a microcontroller, a suite of fragile sensors, and thousands of lines of code at it.
Just throw an Arduino at it and call it a day.
Right. But as systems become increasingly complex, understanding these purely mechanical, pneumatic, and hydraulic feedback loops is more critical than ever.
So synthesizing everything we've looked at today, from squishing acid through synthetic tubes to, translating thermal pulses across a bimetal wire, what is the ultimate takeaway for the engineer at the workbench?
The takeaway is that software crashes. Microchips short out in high humidity. Digital sensors drift, they lose calibration, or they just fail in high vibration environments.
Very true.
But physics is immutable. When the digital layer inevitably fails, it is the physical properties of fluids, the geometric certainty of mechanical linkages, and the unbreakable laws of thermodynamics that must act as the ultimate baseline failsafe.
I love that.
If you can design the physical architecture of your machine to be inherently stable and self-regulating, your digital controls act merely as optimization rather than a single point of catastrophic failure. The machine itself should want to survive.
The intelligence is machined right into the metal. That is a phenomenal perspective to close out today's deep dive. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.